Okay, so today I'm really happy to have with me Patrice Godefroid, a principal researcher at Microsoft. I'm going to now read a little bit about him, of his bio. So he's been at Microsoft in Redmond since 2006, and before that he spent 12 years as a researcher at Bell Labs. There he earned his bachelor's and doctorate, sorry, not there. Before that he earned his bachelor's and doctorate degrees from the University of Liège in Belgium. Patrice is well known for having invented Verisoft, which is the first software model checker for mainstream programming languages like C and C++. And more recently, and something that's going to be a big topic of today's conversation, he co-developed Sage, which is the first white box fuzzer for security testing. And Sage has been credited with having found roughly 1/3 of all of the security vulnerabilities discovered by file fuzzers during the development of Microsoft Windows 7. So Patrice, thanks so much for joining me and welcome.
Well, thank you very much for having me.
All right, so I'll get right to it. So in this class, the class that I'm teaching on Coursera, we're covering common security problems in software like buffer overflows and SQL injections and format string attacks and things like that. And you've worked on automated means for finding and preventing these problems. So I'm curious, given all of your experience, what's your view on the state of the art? What do these tools do well, and what are they not so good at?
Well, I think yes. So over the last 15 years, there have been a lot of progress on these kind of tools. So automatic program analysis tools, and there are, I would say, two main classes, and I hope you would agree with that. First class is static program analysis, and second is dynamic program analysis. So static program analysis tools, they kind of read the code, usually source code, and then they scan it and they kind of try to find all kind of issues with the code, like bugs, like those that you just mentioned. And then dynamic program analysis tools, they run the code. So usually they have the one execution of the code and then do all kind of check during the execution, again to try to find all kind of like vulnerabilities or bugs. And then you can run them repeatedly, and so you can check multiple execution this way. And I think that really, like for instance, for static program analysis, I mean, it really took off. I think I would say around like 2000, there started to be really commercially available tools inside Microsoft. We have a tool like that called Prefix that started to be developed really in the late 1990s and early 2000, and was deployed really a large scale throughout the company. And these tools have found really lots of issues and help quite a bit, and they are used routinely really today. And dynamic also tools have been used for quite a while. So runtime checkers like let's say like Purify, Valgrind, App Verifier. Internally, we have a tool called TrueScan. So these tools also find a lot of bugs and memory leaks and performance issues and things like that. And then in the area of security, also starting in the early 2000, I would say around that time, there have been also a lot of work on security testing, also called fuzzing, basically to try to find security vulnerabilities, mostly in parsers for files and packets. And then there have been also a lot of progress over the years in having more sophisticated techniques, finding more bugs using fuzzing. So, I mean, that's kind of a general answer. So there've been a lot of progress, but there's still room for improvement.
Uh-huh. Do you, at this point, as you say, they've been under development for maybe 15 years. Are there things that these tools are just awesome at? You mentioned they're in routine use.
Yeah.
For what things do people routinely use them versus things that are maybe still somewhere off in the future?
Right. So, so I know a little bit better the area for like systems code, buffer overflows, memory safety. So actually, for like cross-site scripting attacks and like SQL injection bugs, things like that. So I do not know what the ratio of static versus dynamic analysis, but for buffer overflow, memory corruption bugs, etc., both are used extensively. So usually static analysis is used first, earlier, as the code is being written. And now you have variants of these tools that are basically embedded into, I mean, development environment like Visual Studio, and as soon as you type, they can also perhaps flag some errors. And so they are used early on. And so these static analysis tools, usually they are fast, but they can be imprecise. And so, and in contrast, the dynamic analysis tools are used when you can run the code, so after you can compile it, etc., it builds. And so they are run later, and they tend to be more precise, but they only check some execution, typically not all execution of the program. So they're very much complementary, and in practice they are used at different points during the development, software development, and so they are very much complementary. And we're still, I mean, as a community or inside Microsoft, also developing these tools further to improve basically this precision and the type of bugs that they can find and reduce the cost of using these tools.
Okay, great. So, so you yourself have worked on these sorts of automated analyses, both static analysis. So, software model checking in the case of Verisoft, back, and then also since then, white box fuzzing. So, I'm curious, having worked on software model checking for so long, what prompted the switch to working on white box fuzzing, starting with, I believe, Dart, which was a forerunner of Sage?
Right. So I mean, so in my mind, so both Verisoft and Dart and white box fuzzing and our tool Sage that implements white box fuzzing, they are all related to this idea of software model checking, where one wants to try to prove, I mean, to have to exhaustively test programs. In the case of Verisoft, the main source of non-determinism there was due to concurrency. So the goal was to find concurrency-related bugs. And in the case of Dart or white box fuzzing, the goal is to find bugs in data-driven applications. And so there the non-determinism is due to the large input space for data. But the goal is the same in the sense that in the limits, so if you apply into small example or if you let it go long enough, you get verification. So verification means it's a tool. A verification tool is a tool that can not only find bugs but also prove the absence of bugs or a class of bugs under some assumptions. Or a testing tool is just a tool to find bugs. And so, so myself and many others in the research community have tried to basically develop new tools that are inspired by verification techniques in order to define new bug finding techniques, either static or dynamic, basically, like testing-based, super testing kind of techniques. So the reason for the switch in my case is simply because so when I worked at Bell Labs for 12 years, and there a class of very expensive bugs were inside communication switches, like optical switches or CDMA base station or phone switches. And so there you had most of these bugs were due to concurrency issue, reactivity, real-time issues inside really the core of a switch. And these were like very expensive bugs and very hard to find. And that's why a lot of work initially on model checking in the industrial labs at least came out of Bell Labs, because there was a strong interest for these type of techniques, which have been proven to find quite subtle and expensive bugs basically in these type of switches. And when I moved to Microsoft in 2006, here at Microsoft, I would say that as a class, the most expensive bugs that Microsoft faces are probably security-related bugs. And so there, it's not concurrency-related, it's really bugs that are due to malformed inputs. So for instance, Windows client, so Windows that runs on every laptops running Windows, for instance, etc., or PCs, includes support for about more than 300 file formats. So they have 300 file parsers that are embedded in every laptop running Windows, for instance. And so it's a big attack surface in the sense that if you can craft a specific input file and then open it, process it through the software running on your machine, and you can trigger a buffer overflow. In principle, this could perhaps be exploited, and then you could hijack the execution of the process that runs on your machine. And so this is a big problem for Microsoft. Office is the second big target and big customer that we have for these type of techniques, because Office also supports, depending on how you count, but tens, dozens, maybe a few hundred, depending on how you delimit basically, but parsers and sub-parsers, etc. And both Windows and Office are successful products. They have been deployed on over 1 billion machines. So when we have security-related bugs, they are very visible. We need to patch basically a billion machines through like Patch Tuesday kind of bugs, etc. So this is very expensive for Microsoft. Hence the interest of kind of developing and pushing further techniques for finding bugs in this type of application.
So Microsoft, before you got involved with Sage, was using fuzzing technology, and you developed this new approach that was inspired by program analysis to do fuzzing. I wonder if you can characterize maybe the difference between other sorts of fuzzers that Microsoft uses and Sage, and then also maybe the balance of how much time is spent using Sage-style fuzzing today versus maybe before when you got started.
Right. So I would say that there are three main types of fuzzing, and they were proposed in that order. So the first type of fuzzing is the simplest one, is so-called black box fuzzing. So it's random testing. So if you have, let's say, for file fuzzing, you have a file parser. So a parser means here just a program that's going to read that file and do something with it. And so the simplest form of fuzzing, and the oldest one and the most basic one and the more used one, is so-called black box fuzzing. So you take, for instance, a well-formed input file in that format, and then you randomly fuzz, you randomly switch the value of bits in that file. And so there are various variants like byte fuzzing, where you took 1 byte, you do 256 values, then you move to the next one, etc. So you can do the fuzzing. So this way you generate a lot of variants, and then you try to open this file, run the program that reads that file with all these variants, so it takes a lot of machine time, and you hope to find a bug this way, like a buffer overflow, for instance. So that's black box fuzzing. The second class of fuzzing techniques, we call them grammar-based fuzzing techniques. So there, in addition, you have a grammar that represents the input format of the input, that's the format that the application you're interested in to fuzz is supposed to take as input. So for instance, you have like Excel or Word or JPEG or GIF or whatever. And so now you have a grammar that basically constrains the fuzzing a bit more. So you can say, well, you can go through production rule of the grammar, and by construction generate basically inputs that are accepted, that are in the language of the grammar. And then you can also enhance grammar-based fuzzing this way by having heuristics. For instance, saying, well, these 4 bytes, they're really meant to be an integer. And then you can say and try more often like specific value like 0, -1, and even associate probabilistic weight to the production rule of the grammar. So basically, when you go traverse and generate inputs, so you can control basically random fuzzing this way. It's a way to guide random fuzzing and make it much more intelligent thanks to the grammar. So this is also a very popular approach. And the drawback of grammar-based fuzzing is that you need a grammar. And so the grammar-based fuzzing, in some sense, is as good as your grammar to a large extent. And so this has been also used quite a bit, including inside Microsoft. And the third kind of technique, large class of techniques, is what I would call white box fuzzing, which is what we started really developing and here at Microsoft in 2006, roughly speaking. And so there, in white box fuzzing, we run the program. So we have a file parser and a seed file and an input, and then we run the program on that input to see what it does with it. And we do what's called symbolic execution. When the program is running, we also execute that specific execution symbolically. And in this, basically, the outcome of that is to see what the program does with its inputs. So we generate constraints that correspond to tests on inputs. And then later on, we can negate this constraint to try to use a constraint solver to generate new tests that are going to drive the execution of a program through different code paths. And so we call this white box fuzzing because there the fuzzing is not done offline, but really we have to analyze the program and see what it does with its input. And then the tools suggest different inputs to drive the program through different code paths. That's white box fuzzing. There are various variants, of course, that have been proposed and various levels of cost precision. The advantage, so white box fuzzing is more complex, the tools are more complex, but it's still fully automatic, so you don't need a grammar. And so once you have a tool like that, you press a button and essentially it goes, basically. So Historically, I think black box fuzzing was the first and probably started to be developed and used quite a bit in the early 2000s. Grammar-based fuzzing soon came after, like also between 2000 2005 started to be developed. I mean, I'm talking about mainstream kind of fuzzing circles. And then we started with 2006, etc. White box fuzzing. It took us a few years to get traction and get deployed on a large scale. And today we still actually at Microsoft still use the three type of fuzzing techniques in production, with the exception of grammar-based fuzzing, which sometimes we don't have good grammars for some formats. We have so many different formats. Finding the format itself is a hard problem. There have been also attempts to try to automatically generate these grammars and reverse engineering, and sometimes in white box manner. But these are mostly, I think, stayed in research cycles so far. I mean, it's less frequently used. And so grammar-based fuzzing, there are people exchanging grammars on the internet, etc. So for some formats, they are very well covered, and others, they are not covered. And it's labor intensive. I mean, you need to pay somebody who is going to write for weeks, basically, grammars and guess and try. So this is kind of more expensive than black box fuzzing and white box fuzzing in some sense. The increment cost is higher. But today, we use all three inside Microsoft usually.
So they're all, I mean, so I take from that that they all are effective in various ways. That some, for example, I could imagine that in white box fuzzing, you're going to follow, you're driven by the control flow paths of the program, and some control flow paths are they're just hard or difficult to reach. Whereas you might get very lucky when you're doing a black box thing, or maybe you're not so lucky, but because you put the extra effort into writing the grammar, you're able to get sort of deeper into where the program goes, or maybe deeper is the wrong word. You just end up covering different parts of the state space of the program with these different techniques, and so they complement each other.
Yes, I think your intuition is absolutely correct. I mean, this is intuition at the end because we're still trying to figure out what's the really fine print of what technique is good at and what are the threshold, what kind of bugs, etc. But yes, in the end, I think they're still very much complementary. I would love to be able to claim that Sage finds basically everything that other fuzzers can find. And in some cases, I mean, we've done some experiments, etc. But in general, also, the product teams, they don't want to put all their eggs in the same basket, and so they kind of also, if a hacker is going to use a black box fuzzer, you want to also use black box fuzzer because that's what they would find basically. And in practice also, so when we run fuzzing, like in large organizations like Windows, the fuzzers don't run exactly on the same code as well, which make comparison difficult. So for instance, you might first, as a first kind of test, run some like default, like for instance, black box fuzzing, because it's offline fuzzing, it's easier. It's easier to kind of test it on like unstable build and things like that. And later on, you can go to the more sophisticated tools that needs to run perhaps for a longer period of time, and things like that. So it's very much a mixture in the end. But yes, and so absolutely for grammar-based fuzzing, for instance, especially for like very sophisticated languages, I mean, having a good grammar, give you a heck of a head start, basically, to understand what the format is about and how to drive the execution of a program. So in fuzzing in general, we always use seed files, so well-formed inputs that give us also a head start, right? So you can also have combination where you use first a grammar-based fuzzer to generate, let's say, 1,000 seeds that cover the grammar well, and then you use that as a test suite, basically, for white box fuzzing. So we use these kind of techniques as well. I mean, using seed files is also a common practice in the fuzzing world that we also use with white box fuzzing. And so we have also to refresh these seeds and how to kind of try to have more diversity in this test suite also. And there, grammar-based fuzzing can be used also for that. So
I'm wondering, as you talk about the different tools and the history that Microsoft has had with using these different tools, and also the history of automated analysis, having started with Prefix maybe in the late 90s and it becoming into more common use. Sort of what the story was from your point of view. You come into the research division of Microsoft and you just start to develop this technology, and then what was the step that went from a tool, a prototype that you were developing, to getting to the point that now it's being run on, like you said, Office and Microsoft products that are used all over the world. I
Right.
imagine that that story of getting it adopted is going to mirror at least a little bit of story that maybe people taking the class, if they tried to get tools used at their companies, maybe there were certain roadblocks or whatnot that you encountered that maybe they would encounter as well.
Yes. So we started the development of Sage, which tool that can implement this white box fuzzing approach. And we, in 2006, in 2007, we had a first prototype, and we were fortunate to have some people in the product group that were really intrigued and interested in this. But at the beginning, we didn't know how successful it would be. And so we started basically applying it to a handful of and we found bugs that have been there for a long time and that were missed by everything that was thrown at them so far. So that's kind of was a, and then we had there was the manager, so the person at the head of security testing for Windows Client for Windows 7, who and his name is Eric Douglas, and he was actually an early he kind of was early on suggesting that encouraging us to do this project. And at some point, he decided to so he was at the head of fuzzing actually for Windows 7, and then he decided to invest basically more significantly in Sage, and then it was deployed for the first time. And about two-thirds of the file parsers embedded in Windows client were fuzzed for the first time with Sage in the 2008-2009 timeframe. And it turns out that it's a very effective way of finding bugs, especially on binary parsers. And so, as you mentioned earlier, I mean, at the end, to give you an idea, Sage was credited to have found about a third of all the file fuzzing bugs found during Windows 7. And so, because Sage was also the first, I mean, new tool at the time, it was run last, which means that all the bugs found by Sage were missed by virtually everything else, which is black box fuzzing, grammar-based fuzzing when it was applicable, and also static program analysis that was run way earlier. But and maybe, I mean, by missed, I mean that maybe the static analysis tool would have flagged that bug, but among a sea of false alarms, and I do not know exactly why, but in the end, the bug was still there when we fuzzed it. So when we run these tests, basically, when the Windows team ran these tests, and so the Windows 7 now was our first basically big customer. We were also lucky that and this is also something that I recommend in some sense for other companies, and this is a trend very visible inside Microsoft. There's been a trend of centralizing fuzzing. So in Windows Vista, for instance, which was before Windows 7, the Windows team that was doing fuzzing in a distributed manner. So there may be, let's say, I'm just making this up, but let's say 100 group that need to do some fuzzing. Well, there would be 100 fuzzing guy, and they had to grab some machine and do somehow some fuzzing. Starting in Windows 7 client, they decided to centralize fuzzing. But for me, the tool provider was great because I just needed to talk to that specific team, and I got leverage this way. So there, if you Mike are the head of a development team and I'm in the fuzzing group, what we have to do is you have to identify basically, that's part of the process that we use at Microsoft. There has to be a review at the architectural level for your component, where you have to identify your untrusted interfaces, and then you have to give me some kind of test driver and some seed inputs. But in the centralized fuzzing lab, will run the test, run all kind of fuzzer, do all kind of things, triage the bugs, eliminate duplicates, and then I will send you email. I mean, we use bug database kind of thing to communicate, and then I'll send the bugs back to you, basically. And so now you don't have to worry about all this fuzzing business, etc. A bunch of experts are doing it for the entire Windows organization. So at the beginning it was Windows 7, but now Windows 8 moved to the centralized fuzzing. Now we have recently a reorganization where it's operating system groups, including Windows Phone and Xbox, have a single centralized team. And the same trend happened in Office. And so for tool provider, it's great because now I have a few but very smart users. And so for sophisticated tools, it's easier for me to educate a few people than hundreds. Actually, could not do that. Don't have the bandwidth, the time to do that. And then it allows basically more sophisticated analysis to be run as well, because they have a lot of machines available for all kind of, for fuzzing, but also variants basically available.
That's really interesting to hear. So that kind of dovetails into another thing I'm curious about, which is, um, so you've described an evolution of the development process where people are using static analysis all the time. Of course, they're doing unit testing and code reviews and things like they've always done before. And then they also now are adding this very late phase, right? I mean, this is to the point where these things are building, running, and you can hand them off to a third party to do this fuzz testing with them. I wonder, stepping back and looking 5 or 10 years into the future, seeing how the development process has evolved to the current state, where do you think things are going? What potential is there that's in development that's yet to be exploited? How are things going to get better? Are certain practices going to fall away? Can you look into your crystal ball and imagine what things will look like in 5 years?
Yeah, this is a good and tough question. As Yogi Berra used to say, it's hard to make predictions, especially about the future. So I don't know. But one trend that one sees, and not just here, but all externally, I mean, in the market as well, is perhaps having like program analysis of fuzzing services, where you have basically so you can kind of as an individual like company, you might outsource a little bit of these analysis techniques, and perhaps, I mean, you still need the expert for but for the techniques, the tools themselves could be running in like a cloud, for instance. And so now you get economies of scale this way, or you can mine basically, I mean, how you can do more sophisticated analysis, for instance, and find like API usage bugs, or I mean cross-application kind of bugs, and all kind of things like that. So this is definitely a trend going on, and maybe in testing it could also reach that point. It's a little bit, the infrastructure usually a bit more complicated if you do, for instance, Windows, where some of the stuff is really close to the hardware, so it's hard to, you cannot run this on a standard VM, etc. But for higher level application, I mean, definitely it opens up new possibilities, economies of cost, and also perhaps sometimes running more expensive analysis. Another general research comment, I mean, comment about research, or they could also, hopefully, we will continue to see new tools, and especially perhaps trying to combine the strength and of both static and dynamic analysis. The strength of static analysis is fast and can go anywhere kind of things, and always on kind of tools, and in dynamic being precise, very few false alarms, and so that's the strengths of dynamic program analysis, and have more and more of these kinds and package them in a way that it's really usable by either for specific application domain, or hopefully for so large classes of users. So these kind of tools becomes more and more mainstream. So overall, I think there's still a lot of software being written, and of course, and it's more than ever impacting society. Security is very critical to many different type of. So there will be more progress. It's hard to crisply define exactly how progress will happen, but I mean, there is a need, so it should happen.
I'm just thinking about this synergy that you were talking about of static versus dynamic analysis. I'm wondering whether, just thinking about the way things have evolved at Microsoft, that so one point of view might be that there are these very simple, complete, very likely to be correct, low false alarm static analyses that can find bugs really fast while you're developing your module. And this is good because you can't run the code yet. It's not part of a complete application. And they find these bugs, and therefore these bugs get eliminated maybe early on. So I imagine this is sort of what's happening now. But then there are more sophisticated static analyses. You were mentioning verification before, that you might be able to prove that your component sort of does the right thing for some specification of the right thing. And then I imagine that will have impact on downstream use of tools, right? So when the more components you develop, say in type-safe languages, or using static analysis up front, that creates an opportunity for the tools later on, rather than treating every binary is the same. If this binary came from a outcome of fuzzing, even white box fuzzing might be a little bit different. So I think, as you say, it's hard to look and see how this interplay will evolve over time, but it seems to me that there's an interesting opportunity there.
Absolutely, and there's a whole class of bugs. I mean, a lot of development currently going on in developing apps, for instance, for like smartphones and things like that, or they are like browser kind of application. Unfortunately, this is not really my area of expertise, but there's also the world. These are like sub-worlds, so to speak, and I mean, in the sense, the comments that I made, I think, are applicable to all of them, but maybe I was thinking more about systems code and like buffer overflow kind of things, and like networking software, and like file parsers and things like that. And so also absolutely, I mean, in the other like application development for like yeah, apps for like phones, for instance, etc., or for like the web, and so these are also other very specific kind of markets, so to speak. And so there's also a lot of new tools coming up and different approaches there. And so definitely the world is changing. I mean, if you look at the 5-year time frame, it's changing quickly.
Oh, that's very cool. I wonder, so just to finish up, continuing to look ahead a little bit, maybe a little bit nearer term, can you say a little bit about research problems that you or the community working on these sorts of techniques, symbolic execution or whatever that supports white box fuzzing? What are some of the problems that you're looking to solve today?
Right. So there's a lot of work currently being done in this space, you know. But so there are two main. I mean, okay, personally, the way I view it is, or a simple way to see what's going on is twofold. So in the short term here, so one problem is to see how far are we from verification. So sometimes we have run Sage, for instance, for a long time now. So actually, we've run Sage now for a total, roughly speaking, to give you an idea, about 500 machine years. So Sage has been running nonstop on average about 100 machines over the last 5 years. And today, as far as I know, so it's like the largest computational usage ever for an SMT solver, the satisfiability modulo theory solvers. And so, but one thing that's so in some cases we've been running it for a long time, and we don't find bugs anymore. And so now, how far are we from verification? I mean, how can we even improve the techniques, especially the techniques used to deal with path explosion? There's a number of the combinatorial explosion, number of paths that need to be explored in such a way to have complete coverage, even up to some in size of inputs, for instance, etc. So that's one. So it is, of course, related to related approach to program verification, like so-called verification condition generation, bounded model checking, etc., which are other techniques basically that try to take programs and have a precise logic representation of those programs, and then you can, using solver, reason very effectively, very efficiently about the possible behaviors of the program. So that's one direction, is what's the gap with verification. The other is try to find, I mean, short-term, more application domains. So for instance, Sage is used mostly today, still today, for file fuzzing. But now what about packets? What about services? What about unit testing of in general, for instance? What about managed code? So we have another project called PEX here, which does unit testing for .NET code, etc. But so how can we get more usage and users for that? And so try to basically this machinery of using symbolic execution and constraint solver is still very limited to a specific application domain. And so while we're very happy and proud of that success, I mean, this is just the tip of an iceberg or scratching the surface. I mean, most developers at Microsoft do not write code for file parsers. So how do we reach other application domains on your other communities? How can we maximize the impact of this type of research, not just the work that we do here at Microsoft, but as a community, basically? How can we impact the world further in order to continue doing the research, get our funding, etc., of course, also. But and so there, I mean, so like trying to be better at what we do, which is the verification angle, and also trying to make what we can do already more applicable to a larger class of applications and users is another main theme.
Okay, fantastic. Well, I don't have any more questions. Unless you'd like to add, I will say thank you so much for joining us.
Well, thank you very much for having me and giving me an opportunity to talk about this work.
Fantastic. Thank you.